Welcome to the class, and what we are going to see today is basically extension of hard decoding. Now we have discussed hard decoding where it was used in the demodulation block, and what was happening there, we were basically thresholding the received symbol to the nearest constellation point. Okay. Now coding, I briefly said that we could use something called soft decoding and it could give us better performance than hard decoding. So even in the hard decoding, I just said that it is basically like it works according to the nearest distance rule. Okay. I'll show you that how this nearest distance rule is arrived, okay, and then build on top of it to basically give you how soft decision is done. Okay. Right. So that will complete our understanding of this demodulation block. Okay. First part will be like devoted to understanding this hard decoding. We will develop the framework, okay, for how this nearest distance rule is derived, and then we will use this framework to develop the soft decoding. Okay. So if we understand this well, extending it to this is very easy. Okay. So this lecture is sufficient for understanding this. Okay. No other notes are required. And so if you look at it, basically what are we doing in the transmitter and the receiver part? Okay. So what happens is, if you look at in this complete schematic, what have I done? I have abstracted the transmitter and the receiver part. When I say this abstraction is, I have combined all these blocks, okay, and then taken the input and then given the equivalent output. Okay. So what is this? Basically, what is this transmitter? What are different blocks of transmitter are in principle doing? Okay, they are taking a message, okay, right, some information bit which is transfer block which needs to be transmitted, and finally what is happening here is it is modulated, mapping into some symbols, correct? So that's what I am writing over here. Some message is being mapped into some symbols. Okay, they can be QPSK, 16 QAM, 64 QAM, they can as well be BPSK symbols also. So in this study we will restrict ourselves to like BPSK, but this is applicable for all modulation levels. Okay, right? So you see this, for corresponding to each message we are mapping it to a particular symbol. Okay, that's it. So this is whatever processing you do, right? Okay. So what is happening at the end of it, you are taking certain bits, mapping it to some symbols. Then what happens after that is you have R is equal to S plus N. This is our AWGN channel on which the symbols are being transmitted. Okay, noise gets added. Now this receiver has to basically decide based on the received signal what message M hat was transmitted, right? Okay, and that's the job of the receiver, correct? And finally it has to give you the, whatever way it processes, it has to give you this message back, correct? Okay. That is the abstraction of the receiver. So before we develop this receiver, let's understand this, the model of thermal noise. How does this work? Okay, how is this model? Okay, so basically caused by a random motion of electrons in electronic components, and there are like millions of these random electrons, and you don't know how they are moving. Okay, so now they are all like they move in random direction, and then what does the central limit theorem tell us? You add all this like random like numbers, okay, right? And what it gives you is that those sum of those random quantities, okay, can be modeled as Gaussian, okay, because there are like millions of these random quantities which are being added, okay, correct? So this thermal noise is modeled as Gaussian due to central limit theorem, okay. So that's the reason we use this additive white Gaussian noise channel, okay, and it is of the order of 10 to the power minus 15 watts in a mobile phone. And why does this become relevant? That is the first question we need to ask. And what happens is, these mobile phones, they are designed to operate at a received power of 10 to the power minus 14 watt, as low as that, okay. And just to give you an example, that your mobile phone, when it transmits at a power of 250 milliwatts. Okay. By the time it reaches the base station, its signal strength would have deteriorated that much. Okay. So depending on the distance, okay, and then you look at it, the signal power is becoming close to the noise power. At this signal power, that is only 10 times stronger than the noise power. So now the noise is becoming relevant, right? Okay. So you have to consider this. That's where this AWGN channel comes into picture. And what is our design? Basically, to design, what is our objective? Objective is to design this optimal receiver for this communication system. Okay. And what do we mean by optimal receiver? Okay, the optimal receiver will basically maximize probability of correct decision. Okay, and it makes sense because we want to maximize the probability of correct decision. Okay, whatever this m hat is being detected over here, its probability of being detected correctly should be maximized. Okay, that's the job of the receiver. Now, that's the basic framework wherein like the receiver needs to be developed. Okay, now as I said earlier that we will restrict ourselves to this binary shift keying in this understanding. Okay, and then but this is applicable for any QAM 16 QAM or any other higher order modulations. So what we are saying here is that the system transmits either message M0 or M1. Okay, so binary, and then it transmits this message M0 with some a priori probability P of M0 and M1 with probability P of M1. What does that mean? That it is not equally likely that there will be like the probability of transmitting M0 is different from probability of transmitting M1. Okay, and these probabilities are basically already known to both transmitter and receiver. Okay, what is not known is whether M0 is transmitted or M1 is transmitted, and this noise is statistically independent of this transmit message. Okay, right, because this is imposed onto us by the nature, and nature doesn't like bias whether is not biased whether M0 is transmitted or M1 is transmitted. Okay, and this noise, okay, because this has Gaussian PDF, is Gaussian. Okay, what will its PDF be? This is the PDF. Okay, and this, if you look at it, what is this PDF telling us? That what is the power of this or the variance of this Gaussian? It is sigma square, and the mean of this is basically 0. Okay, right, and so this is the PDF of the noise. Okay, and it has a Gaussian PDF. So this is BPSK, where M is either M0 or M1. Now what is this, the decision rule which is going to maximize the probability of correct decision, okay, or minimize the probability of error? What is it called? Maximum a posterior probability. Okay, and what is this? Okay, look at this carefully. What are we how are we like defining this rule? We are saying that declare this estimate of the message as M0 if, look at this, P of M0 given you have received R is equal to rho. Okay, what is this? This is the a posterior probability of M0 being transmitted. Okay, why are we calling this as a posterior probability? A posterior is basically the probability after the event has happened. Okay, and how are we, if you keep this in mind, how are we calculating this probability? Probability of M0, of message M0 given this event has happened, right? Okay, and that's what is the a posterior probability. Okay, so and how are we maximizing it? We are basically like calculating two different probabilities. Probability of M0 given this signal is received, okay, and we are calculating this probability of M1 given this signal is received. So we will calculate these two numbers, okay, and we will say that M0 was transmitted if this probability is greater than this posterior probability, right? Okay. See, there are two different probabilities. One is a priori probability, which is basically the probability of transmitting a message, okay, even before any event has happened. Okay. This is, which are given as P of M0 and P of M1. And what is this probability? This is a posterior probability, which is the probability which is being calculated after an event has happened. And what event has happened? Basically, the receiver has received the signal. Okay, as I said, these a priori probabilities are known to both transmitter and receiver. Okay, that these messages are being generated with this probability. But what is not known is basically whether M0 was transmitted or M1 was transmitted. Okay, and how is it calculating? And this is calculating, receiver is calculating the a posterior probability. Okay, and maximizing it. It's only picking up M0 if this probability is greater than this, which is basically maximizing. It is picking up the maximum value. Okay. So now what is this from here to here? Okay. How have we written this? If you remember the basic Bayes rule, okay, right? That's what we are using over here. On both sides, let's explain this first. This part is parallel to what is written over here. Okay, correct. So what is, if we write, what is if x and y are two event or two what? Okay, so how can we basically write this? Okay, so what is, can we write it like this? Right? What is this? P of x comma y, right? This is also P of x comma y. That's what I am writing. Okay, so if you look at this, so how can we write this? P of x comma y is equal to P of y given x, P of x divided by right. Okay. So if you carefully look at this, what are we doing here? We are doing the same thing. Okay. So if you treat this as x, you treat r is equal to rho as y. Okay. What am I doing here? Okay. X given y. Okay, I am writing as y. I am given x, probability of x divided by probability of y. Correct. Okay. The same thing I am applying over here. Okay. So, and I am r is equal to, instead of writing r is equal to rho, I have written rho over here. Okay. Same we have done over here. Okay. Similarly, this will also follow. You will basically write the, you will use the Bayes rule to expand it like this. Okay. Fine. Then if you look at this now carefully, what is sitting in the denominator, okay, is same on both sides. Okay. And it is, both of them are positive. Okay, so you can conveniently cancel them without changing the inequality. Okay, so that's what I have done now. Okay, so what have I done? I have basically simplified this and I have written it like this. Okay, why have I simplified it like this? Because I know this is given to me. P of m0, I know Pm of m1, and next I am going to show you that this is very easy to calculate. Okay, P of r given rho given m0. Okay, right. So what is, we use Bayes rule, okay, to move from here to here. Okay, what is this? You should also notice this. This is capital P. This is discrete probability. Okay, discrete probability because messages are discrete. Okay. Now what is this? From here to here. When I write P, this is rho. If you look at this rho, okay, what is this? This is a receive signal, and what is happening over here? We are adding noise, Gaussian noise. Gaussian noise is a continuous random variable. Okay, so from here to here, it has become discrete. It was discrete and it has become continuous. Okay, so this notation is for continuous random variable. This notation is for discrete random variable. Okay, and this is binary P of m0 and P of m1. Okay, now I'll have to calculate this. Okay, and once we calculate this, the calculation of whole of this becomes very easy. Okay, and that's what I'm going to show you. Okay, so now one more fact. Okay, that this basically the map rule. This is the map rule, right? Okay, it becomes maximum likelihood rule when messages are equiprobable. What happens when messages are equiprobable? What does that mean? P of m0 is equal to P of m1. Okay, and that also gets cancelled. So then what are we maximizing? This, and what is this? This is called the likelihood. Okay, right? From a posterior probability, we have moved to the likelihood. Okay, so this is, if you maximize only this, this is called the maximum likelihood rule. Okay, so another key thing is map reduces to ML when messages are equiprobable, and the reason is this. This is map and this is ML, likelihood. Okay, so now what are we left with? Okay, if you look at here, going back, we need to calculate this. Okay, this PDF of a continuous random variable R. What is R? R is basically S plus N, right? And I have to calculate this continuous distribution for row given M0 and row given M1, okay. So you will see this, I will combine both of them, basically use the same notation. When I say combine, I will use the same notation. And what is this notation? Row given Mi, okay, and Mi is basically, okay, it should be for 0 and 1, okay, that's the typo, it should be row given M0 and row given M1, okay, right. So we need to calculate this, okay. So how do we calculate? So what are we saying? If you look at this signal, okay, so how do you read this? What is this probability? This is a conditional probability, right? Condition on given whether the transmit message was M0 or M1, right? Okay. So what is it saying? Mi is given to us, okay. Now if Mi is given, we of course know S also, okay, whatever S was transmitted, okay. So what are we saying? Okay. So with a given Ri, with a given Mi, if you look at this, how will you calculate this? Okay, R is equal to rho is obtained from N by adding a known constant S of I, okay. So let's look at this. I'll just explain it to you. So what is being said in this bullet is as follows. Okay, what are we saying? That given Mi, okay, what is this? What is our signal model? R is equal to S plus N, right? Okay, correct. Now what do we need to calculate? We need to calculate this PDF, right? And what is this? This is a conditional PDF and condition on M of I. What is the meaning of conditionality? It is basically given to you, okay. Now, so what are we saying? So we have been told to calculate this PDF that the message was either M0 or M1. So what is the PDF of R? PDF of R is basically what is R? R is being generated by adding known constant S to some random variable N, because it is given, right? Okay, it is given. So then what is R? To summarize, R is basically derived by adding a known constant S of I to N. What are we referring to S of I? S of I is basically this, right? For a given M of I, S of I is generated, okay. So we know what S of I is being transmitted if we are calculating this probability, okay, right. So what are we saying here? Now if this is the case, okay, what will be the PDF of R? How are we generating R? It is being generated by adding a constant S of I, okay, correct. So what will be the PDF of R? If you basically, this simple random variable, okay, transformation of random variable, that if you add a constant, okay, to another random variable, what happens? The PDF actually shifts, okay, right. And how much does it shift? It shifts by the known constant, okay. And so what are we saying here? Okay, that this PDF, read this carefully, this is the PDF of R, right? And this is what we intend to calculate, okay. And what is this PDF? This PDF is equal to the PDF of noise, okay, which is shifted by a constant S of I. This is the PDF of noise shifted by this constant S of I, okay, right. And why are we able to do it? Because we are given Mi. Correct. So this given Mi is coming here, this given Mi is coming here, okay, right. So this PDF of this received signal is equal to the shifted PDF of the noise, okay. And how much it shifted? It shifted by S of I, okay, right. So now what happens is, as we said in the beginning of the class, that this message M of I is independent of the noise, or the noise is independent of M of I, okay, right. So from here to here, what have I done? I basically, because M of I is independent of N, I have dropped it, okay, right. So if two random variables are independent, if X and Y are independent, P of X given Y is equal to P of X. That is what I have written. N and Mi are independent, so I have dropped M of I. So this PDF is basically equal to the PDF of this noise, right, okay. And we know the PDF of the noise is a Gaussian PDF, okay, right. Basically calculated this PDF, P of R, and how is it calculated? It is basically the PDF of the noise. So let's use that, okay. What is our map rule? This is choose M hat is equal to M0, okay. How will you choose this? P of rho given M0 into P of m naught. Okay, this is map. Okay, I am still not assuming that P of m naught is equal to P of m1, right. Okay. So, what does map rule say? Choose m naught if this probability is greater than this probability, correct. And what was our objective? Our objective was to calculate this PDF, okay, and I calculated exactly that on the last slide. Okay. This is that PDF which had to be calculated, and this is the PDF of the noise. Okay. So, if you look at it, what is it coming out to be? P of n, PDF of noise shifted by, what will happen here? It will be shifted by S naught, and this is that probability. What will happen here? PDF of noise now shifted by S of 1 into multiplication, and this is the a prior probability, right. Okay. So, what do we have now? Okay. Just substitute it over here, correct. Okay. This is what was our PDF of noise. It was a PDF of, it was a Gaussian PDF. Now it is shifted by S naught, okay, right. If you recall, what was the original PDF? It was 0 mean, right. Okay. And how did we write it? Exponential minus rho square by 2 sigma square. Now what has happened while calculating this PDF? It is now shifted by S naught. So this shift, this is the mean, correct. So this is rho minus S naught square by 2. So this is come out to the mean. This is S naught is mean over here and S1 is mean over here, right. Okay. So what have we achieved till now is basically, what did we do over here? We basically looked at this Gaussian channel, okay, and we have abstracted this transmitter and receiver, okay. And what is this transmitter doing? Basically, it is taking in some symbols, and then it is taking in some message bits, and then it is basically giving us some symbols. And then what is this receiver doing? What is the job of the receiver? It looks at this received signal R and then tries to estimate m hat, okay. And what is the rule we are looking at, which we claim that it will maximize the probability of correct decision, which that is basically the maximizing the a posterior probability, okay, right. And what we have done till now is basically simplifying this, the PDF of the received signal, okay, in terms of the PDF of the noise, okay, correct. And it turns out that if you use simple Bayes rule, this PDF of the received signal becomes the PDF of the noise and shifted by whether M0 was transmitted or M1 was transmitted, okay. Now in the next class, I am going to simplify this for you and show you how this rule actually reduces to the nearest distance rule, okay, right. And then we will build on top of that. We can spend some time for us to understand how this framework leads us in calculating the soft values of the transmit bits, okay. So with that, it will close the discussion on the demodulator design, okay, right. And why are we doing this exercise? Because two things. Last time when we discussed about demodulator, I just told you without going in detail that this basically the demodulator works on the principle of minimum distance rule, but we never discussed how that minimum distance rule is actually derived and then how this soft decision rule is implemented, okay. So we are doing all this exercise to understand those two aspects, okay. So I'll stop here, then we'll continue discussing this in the next class. Thank you.